point A to point B. Often, the transport of bulk solids is also called as conveying of solids. Conveying of the solids. Because the gases and liquids, there's a continuous transport. There's a continuous connection between the molecules, and that makes the whole transport is easier. Whereas solids transport is basically taking out one by one. You are not, there is no any continuity between the individual particles, although we are transporting continuously. That's why they called as conveying of solids. So the conveying of solids are basically three types. One is uh, one type is called continuous mechanical conveying. Continuous mechanical conveying. This type of conveying is used when the bulk solids are very big, like few centimeters in size, Often, this continuous mechanical conveying is open atmosphere, like whatever the transport of solids is often open to the atmosphere. So, solids which won't, like if the particle size is very small, it can form dust easily. They can form dust easily. So, you will lose the material during the transportation. So, that's why the continuous mechanical conveying is used to transport the bigger solids, usually in the centimeter scale. Usually in the centimeter. If you pass by any chemical industry or any port, you would definitely see these continuous mechanical conveyors. So I have listed three types of continuous mechanical conveyors here, but there are a few others also, which are all similar principle. So that's why I haven't listed all the names. The first type, the first and most commonly used for the continuous mechanical conveying is belt conveyors. Belt conveyors. Another type is screw conveyors. Another type is screw conveyors. And another type is bucket elevators. I'm going to talk about these three in the next slides. So another one is called pneumatic conveying. Another type of conveying of solids is called pneumatic conveying. Pneumatic conveying, the name suggests that transportation of solids or conveying of solids with help of air or any gas. With help of air. If it is reactive with oxygen, usually we use inert gas, nitrogen. We transport the solids with help of the inert gas like nitrogen. That's called pneumatic conveying. We'll also talk about pneumatic conveying in detail. Then hydraulic conveying. Transport of solids in the form of slurries. Transportation or conveying of solids in the form of slurries is called hydraulic conveying. Hydraulic conveying. So, usually these two, pneumatic conveying and hydraulic conveying, are closed because we basically transport through the pipes. We'll transport through the pipes. Advantage with pneumatic conveying, hydraulic conveying is that this is closed transport. So you will not lose any materials. Like it won't form any dust. You are not going to lose any particles in the form of dust. Whereas continuous mechanical conveying, this one is open to atmosphere. This one is open to atmosphere often. We can do in closed conditions also, but there's a high chance of dust formation. Right? And you can use pneumatic conveying only for the fine particles. Only for the fine particles. It has to be less than 100 micron size. If you want to use pneumatic conveying, hydraulic conveying. Why? As you learn later, that for the transportation of, like when you want to transport of solids with help of gas, basically we blow the gas and for the movement of the particles. If the particles is bigger, we need to blow a lot of amount of air with high amount of energy. So that's why if the particle size is bigger, if you use pneumatic conveying and hydraulic conveying, the energy requirement will be very, very high. So for the bigger solids, continuous mechanical conveying, and which solids it doesn't lead to the formation of dust, we will use continuous mechanical conveying. For smaller particles, we use pneumatic conveying, right? So I will talk about more other advantages, disadvantages when I talk about pneumatic conveying. Basically, the quick way to understand which one to use when, that is the big classification. Smaller particle size, pneumatic conveying, hydraulic conveying. Bigger particles, continuous mechanical conveying. Continuous mechanical conveying is open to atmosphere, so it should not lead to the dust formation. Okay, so one example of here, what is the typical belt conveyor? So the belt, the name suggests that we are conveying the solids with help of a belt. We are conveying the solids with help of a belt, right? So I just shown few images, few types of belt conveyors here, and here see this is a belt. This is the belt, and here they place the solids, and as these wheels rotate, the belt will move, and it will move between the point from A to B where you need to transport the solids. That is very simplest. Other types of flat belt, inclined belt, curved belt. I am sure nowadays most of you would have traveled to the flight by this time. If at all you gone to the airport, you will see the belt conveyors when you depart, like when you reach the destination, when you collect the luggage, they actually transport the baggage through the belt conveyors. That is as simple as the belt conveyors. So just simple. As the wheels rotate, or as the gear rotates, the belt will move. As the belt moves, whatever solids present on the belt, that will also move. And that way, the transport of solids takes place through the belt conveyor. So, as I said, these solids are subjected to the open atmosphere. That means open wind currents. So, wind might move from one point to another point. If the solids can form dust, which if the solids are very fine, and as the wind blows over these particles, the particles can convert to dust, and you might lose the particles. That's why belt conveyors are not suggested to use the fine particles. Another type of the continuous mechanical conveyor is bucket elevators. See, basically, there will be a continuous belt. This is a belt. This is a continuous belt. This one belt, and to this belt, buckets are attached. Just like this. You can see small buckets are attached, and there's a chain. That basically, as the chain rotates, the buckets will move up and down. So, at the feed point, the buckets are filled, and as the gearbox rotates, the chain rotates, and the belt rotates, and the buckets will move. Upward, and when it's come to this discharge point, that is, it's tumbled down, and the solids are emptied. And taken down. I'm sure nowadays in most of the building construction people, they're using these bucket elevators to transport the concrete mixture from ground floor to the top floor. I'm sure you all know it. Just a simple video how the buckets move. So these are the buckets which is moving from top, and when it is reversed and is tumbled down and gets emptied. You can see now this is loaded, the solids loaded, and it's getting emptied. So this is the simplest, very simplest bucket elevators. And as I said, when the particles are bigger and which won't form any dusting, then we can definitely use these bucket elevators, and which is simple and cost effective. Another type of conveyors is called screw conveyors. It's just as the name suggests, there will be a screw which rotates. As the screw rotates, the solids will move from one point to another point. The solids will move from another point to another, one point to another point. Here I have showed a simple screw conveyor. You can see this is the feeding point, and this is the feed point where the solids are dropped. And because with help of this motor, the screw is rotated continuously. The screw is rotated continuously. When the screw moves from the bottom to up, the solids are carried away with the help of this screw. The solids are carried away with the help of the screw. That way, the material is moved from one point to another point. This is the feed point and this is the discharge point. Very, very simple. Again, I just put a small video to understand easily. And here the screw, and which is loaded with the sand, and you can see as the screw is moving, the solids are pushed. The solids are pushed or carried by the screw. The solids are pushed or carried by the screw. This way, the sand is being transported from one point to the other point. The sand is being transported from one point to another point, and it's collected at the discharge point. This is just only a simple demonstration conveyor, and this is usually used for the short distances. Screw conveyors can only use for the transport of solids for a short distance. Transport of solids for a short distance. Now, screw conveyors can be used for the fine particles. Screw conveyor can be used for the fine particles, and it will be operated. It can be operated or it will be operated in a closed conditions. But only disadvantage is it can only done for the short distances. It can only done for the short distances, and it can only handle small quantities. It can only handle small quantities, right? So these are the continuous mechanical screw conveyors. These are the continuous mechanical screw conveyors. So if the particles are very fine, as you can observe, whether in bucket elevators or belt conveyors, they can easily form the dust with help of the wind currents. So how to transport, how to do transport for very, very fine particles, which can easily, that can easily mix with air, even at low wind velocities, how to transport them. For transporting such things, we use pneumatic conveying. For transporting such things, we use pneumatic conveying. So here, the continuous mechanical conveyors are very, very simple mechanical instruments. It doesn't need any details of chemical engineering fundamentals to design it. They're very, very simple. Depends on the size requirements. We can design a belt size, or we can design a belt or bucket size, or we can design a screw size. So these are very, very simple. So that's why I'm not spending. I don't want to get into this design aspect because they're all simple mechanical equipments. So now, yeah, thank you for recording. I forgot. So now we'll move on to the pneumatic conveying. So I will share from other thing. Just give me a second. What happened? Ajay Raj Meena. Join now. So I'm sharing whiteboard because I wanted to um, just write on the board as I teach, rather than just showing the PowerPoints, because one or two derivations are there in this topic, and I could not figure out, I could not find good images and videos for this part. So I thought I shall explain using the board. As one student suggested to use a better device for the annotations, I thought to use this whiteboard, and so probably this will help just experimenting for the first time. So,
Sir?
so next we talk about is pneumatic conveying. So, too bad. So pneumatic conveying means transportation of particles with help of air. Transportation of particles with help of air. Let's say this is the pipeline. Let's say this is the pipeline, and we have a feeder. We have a feeder, and through which particles can be fed into the pipeline. Through which the particles can be fed into the pipeline, right? So the particles, the fine particles, they will just fall. They will just fall into this pipeline. As you are feeding the particles with the inlet, and if you blow air, if you blow air, if you blow air, what can be done? What it can be done? What it can be done? This air can carry the particles. The particles can nicely disperse. The particles can nicely disperse in the air. The particles can nicely disperse in the air, and they can flow along with the air. They can flow along with the air. They can flow along with the air. So such transport of such mechanism, the transportation of such mechanism is called pneumatic conveying. Is called pneumatic conveying, right? However, this is not so simple as I explained. It is not so simple as I explained. This can be a very someone getting error. 1 second.
Yes, sir. I have got error.
Is still something went wrong?
Sir, it is showing that your whiteboard will not be recorded.
Whiteboard will not be recorded.
Yes, sir. It is
Oh.
showing. It is not there in the MS Teams.
Sir, maybe you can use in PPT or in MS Words. You can draw.
So you can use
you
the
can use
iPad also
Blackboard also.
if you are
Yes, sir,
having.
that will be fine.
So I am using
You could go for Paint.
Paint.
So in the
Okay.
iPad, that
Sir,
the
using
note
Excel-
section you can use.
Sorry.
So you can use, OneNote, or you can use the blank slides of the PPT. That will be better.
Okay, okay. Sure, I will do it. So I will use PPT. Yes, cannot record this.
Sir, you can share your screen and then share the whiteboard as an app, not directly share the whiteboard.
Oh, right.
When
I
you
think I will do
sharing,
PowerPoint.
it will be recorded.
Share PowerPoint. No. Just give me 2 seconds, then I'll just. Time wasting. No. Why did I do it today like this? Yeah, sorry students for the delay. This is also not so good. Are you able to see everyone?
Yes.
Yes, sir.
Yes, sir.
Okay. So probably I will have to write a little bit slow. So what I am trying to say is pneumatic conveying, transport of solids with help of air. So we have a pipeline. Let's say we have a pipeline like this. To this pipeline, we have a feed point. We have a feed point. Through this feed point, the solid particles sent inside the pipeline. The solid particles are sent into the pipeline, solids. So let's say the solids are just falling, solids are falling down, the solids are falling down from the feed this way. At that time, if you blow air, through this, what will happen? If you blow air through this, what will happen? All these particles will be uniformly dispersed. All these particles will be uniformly dispersed and move along with the air. All these particles will be dispersed and move along with the air. They move along with the air. So this way, the solids are transporting from a point A here to the point B, wherever it required. So such type of transport of solids is called pneumatic conveying. Pneumatic conveying. The name suggests conveying with help of air. So that is a very simple explanation of what is pneumatic conveying. Now, now what happens in the pneumatic conveying? What are the parameters we need to look into? That we will see in the rest of the class today. There are two types of pneumatic conveying. One is called dense. One is called uh, dilute. One is called dilute, D-I-L-U-T. One is called dilute pneumatic conveying. Another one is called dense pneumatic conveying. So, in the dilute pneumatic conveying, the concentration of solids is low. That's why we call dilute, right? When we call dilute, when the concentration is low, that we call dilute pneumatic conveying. If the concentration of solids are very high, that we call high solid content. That we call dense pneumatic conveying. Now, when do we use pneumatic conveying? When we should not pneumatic conveying? Let us see that one. So when can we use pneumatic conveying? That is the important part. So when do we use pneumatic conveying? If the particles are fine size. If the particles are fine. Fine in the sense micron size. Fine in the sense micron size. If the particles are in micron range, then we will go for the pneumatic conveying. As you understand just now, we are basically pushing the solids with help of air. If the solid particles are bigger, right, we need to blow air. We need to send air at high velocities. What is the problem with sending air at high velocities? More amount of speed required, right? We all have a fan, right? We all have a fan. If you operate at high speed, the fan can give high amount of wind currents. But at the same time, it consumes more energy. It consumes more energy. If the fan rotates at slow speed, definitely it consumes the lower energy, right? We all know that they use blower to blow the dust in the roads. Nowadays, we use a blower to, if any leaves or any particles, dust is standing on the road, they use blower instead of the broomstick. Now, if you want to blow large amounts of big particles, then we have to blow with more amount of energy. If the particles are bigger, that consumes higher energy. If the particles are smaller, consumes less energy. That's why the fine particles are used. Another advantage with this is a closed. We are basically transporting in a closed pipe. So hence, if there is no loss of material will takes place. There is no loss of material will takes place during the transportation. So these are the two advantages. Fine particles can be transported, and there won't be any losses during the transportation. But what are the drawbacks? What are the limitations of pneumatic transport? We have to also understand that. If particles, let's say in the pneumatic transport, this is the pipeline as I just showed, the particles are suspended. The particles are suspended, right? The particles are suspended. Now, when they move, attrition, the collision between particles can take place. Attrition. The first problem is attrition. Attrition. So, if you have any fragile solids, brittle solids, right? If the particles are brittle or fragile, then obviously this attrition leads to the change in the size. This attrition leads to the change in the size. So at the feed, you have certain size of the particles. At the discharge, you will have the completely different size of the particles. So if the particles tend to break easily due to the nature of the solids, pneumatic conveying is not advisable. That is one. Another one, suppose if the particles are of the sharp-edged shape, if the particles are not a smooth granular solids, suppose if the particles are not a smooth granular solids, then usually they might have a sharp edge like this. When the sharp edge particle flow over this pipeline, some of the particles will interact with the wall. Some of the particles interact with the pipeline wall. So these sharp edge particles can create some abrasion, some rough surface, and with the time, it can damage the pipeline. With time, these sharp edge particles can damage the pipeline. So if the particles are abrasive in nature, and if the particles are sharp edge, then obviously pneumatic conveying is not suggestible, right? And also, as we discussed in the previous classes, adhesion forces, cohesive forces. If the material tend to be cohesive, if the materials tend to be cohesive, that is sticking to each other, there is a chance of blockage. blockers. If the particles are cohesive, that is, they tend to interact and they tend to join together and can form a big agglomerates, and that agglomerates can cause the blockage of the pipelines. That can cause the blockage of the pipeline. So if the particles in nature is attrition, if it is fragile or it is brittle material, then pneumatic conveying is not advisable. If the particles having the sharp edge, then it is also not advisable. And if the particles are moistened and adhesion forces are strong, which leads to the cohesion between the particles, that can cause the blockage of the pipeline. If doesn't blockage, then still we can use the cohesive solids. Still we can use the cohesive solids. So that is the advantages and disadvantages. That is, when can we use pneumatic transport, when we should not use pneumatic transport. That I have explained here. Students are able to understand what I am trying to explain.
Yes, sir.
Yes, sir.
Yes, sir.
Sir, I have a question.
Yeah.
So when we use the dilute pneumatic convey and when you use dense pneumatic convey?
Oh, when do we use dense pneumatic convey? When to use dilute, right? That is your question.
Yes, sir.
Yeah. So at all, like if the particles are cohesive nature, the particles are cohesive nature, by default that will go to the dense pneumatic conveying, because even though you at the inlet you might have the dilute conditions, but as they flow, the particles can join together and form the dense pneumatic conveying. That is one. Second one, if at all you want to transport, if at all you don't want less attrition, if you want less attrition cannot be avoided, but there could be minimal. At some cases where you want minimal attrition between the particles, then we use the dense phase pneumatic transport. If at all you want the minimum attrition between the particles, then also we use the dense pneumatic conveying. So when do we use dense pneumatic conveying? If you want to minimize the attrition between the particles, right? If you wanted to have very less attrition, then we have to use dense pneumatic transport. If the solids are cohesive, by default it will go through the dense pneumatic transport. If the particles are not cohesive, you don't worry about attrition rates. We prefer dilute pneumatic transport. Did I answer your question, Subhajit?
Yes, but sir, I have a question that when the particles means when we want less attrition, then why we use dense means pneumatic convey?
Yes.
Because then
If
the
you
particle density is greater, na?
Yeah. You will understand when I'm trying to explain more details of dense pneumatic transport. I haven't even explained, right? What is dense, what is dilute. So you will understand. You just hold on for a few seconds, or not few seconds, few minutes. Probably you will understand better.
Okay, sir.
Yeah. Any other questions? By the way, any other questions based on what we discussed? No questions. Good. So what is dense dilute pneumatic conveying? What is dense pneumatic conveying? That is the question we have to understand, right? So I already showed what is dilute pneumatic conveying. So we have a pipeline. So we have a come on. So we have pipeline. What's that? Sorry, students. I think I made a mistake by relying on my tab. Will not do next time. I will stick to my own PowerPoint. I attempted when students suggested to use this, so I have attempted, but I think I'm not that good in this. So next time I will not do this, and I will not cause this inconvenience to you. I will go what I'm best, that is preparing more in PowerPoint and proper annotations. Okay. So dilute pneumatic transport. Sorry. Yes. Why it's not allowing me to write? So in the dilute, the particles are dispersed uniformly in the air. The solid particles disperse uniformly in the air.
Sir, are you talking anything? Because you are muted.
Are you able to hear now?
Yes, sir.
Yes, sir.
Oh, sorry. Thank you, Subhaji. Okay. So I'm actually explaining dilute transport, dilute pneumatic conveying, and dense pneumatic conveying. In the dilute pneumatic conveying, the particles are dispersed uniformly. The particles are dispersed uniformly as shown before, right? So this is dilute pneumatic transport. One type of dense transport, one type of the dense transport, a bunch of particles club together, the bunch of particles club together and they move. The bunch of particles club together and move. It is like a bunch of particles just moves and there'll be some space and you will have air in between. And this way the particles will tend to move like a plugs, like a bunch. The particles will move like a bunches rather than individual particles. A bunch of particles moving, a bunch of particles moving through this, and we have air in between, and that air pushes the particles. Air pushes the particles. Since the solids are flowing like a bunches, solids are flowing like a bunches, and attrition between the particles will be very, very minimal because particles will not hit each other. Like one big agglomerate of solid is just moving. The big agglomerate of solid is just moving instead of the individual fine particles. Okay. So the advantage with this is that you can minimize attrition. You can minimize attrition, but you need high pressure to push the solid. We need high pressure to push the solid, to transport the solid particle. Whereas this required then dilute phase pneumatic transport required high velocities, high velocities. And this requires high pressure but low velocities. High pressure but low velocities. Since we are operating this at low velocities, delta P is function of velocity. Delta P, the pressure drop across this pipeline, is function of velocity. So high velocities leads to high pressure drop and low velocity leads to the low pressure drop. Although this required at the initial input requires high energy, but overall delta P will be lower for the dense transport compared to the dilute transport. Now, so that is the differences between the dilute and dense pneumatic transport. So since this is this is flows like a pack of solids, when the cohesive forces are high, adhesive forces are high, then only the particle tend to form such thing. The particle tend to form like a dense plugs or dense bunch of solids. If the cohesive force is very, very low, then you will not be able to achieve dense type of pneumatic transport. You have to only do the dilute pneumatic transport. Okay. Subhaji, do you understood now what is dilute and dense transport? They answer question. If not answered, please let me know.
Yes, I have understand.
Okay. So now, how do we design in such pneumatic transports? What are all the factors we need to consider designing such factors that we will see now? So, now we have a silo. So this is the silo, right? And from which the particles are coming down. From which particles are coming down. And from this storage area, the particles needs to be sent. The particles needs to be sent to a furnace. There is some furnace here. So how do we transport furnace? This is furnace, Furnace. So the particles needs to be transported from here to here, furnace. So depends on the particle size. If the particle size are lower, then we go for the pneumatic conveyor. When do we use? Like you may say, can you give an industrial example? I can give an industrial example. So in the steel plant, any steel plant where they make iron from the iron ore, like whenever there is a steel plant, they make iron from the ore, right? Iron from the ore. So this ore contains many impurities along with the iron. Impurities. Many impurities along with the iron. So in steel plant, iron, right? In the steel plant, what they do, they heat this ore. They have to heat this ore at temperature higher than 1100 degrees centigrade. At temperatures higher than 1100 degrees centigrade. Why do they need to heat it? Because when you heat at this temperature, this iron melts, whereas impurities won't melt. Iron melts, but impurities won't melt. But how to heat? How to heat this ore? How to heat this ore at such a high temperature? How to heat this ore at such high temperature? Right? That is the question. So how do they heat? So they They do this heating. They do this heating with help of in a container called blast furnace. In a container called blast furnace. Blast furnace. Blast furnace. They heat this iron ore with help of coal. Sorry, CO. Coal. Coal is converted to coke. Coal is converted to coke. This coke will be supplied to the blast furnace. We all know this carbon reacts with oxygen and forms CO2. And since this is an oxidation or combustion reaction and forms heat, since this is a combustion oxidation reaction and combustion reaction, it forms heat. So they supply coke particles along with the ore. They supply coke particles along with this ore, right? They supply these coke particles along with this ore in the blast furnace, to heat the ore. So this is the blast furnace, big furnace, and they feed coke, and they need for the combustion, they need oxygen, that is air. They need oxygen, that is air. In the oxygen, in the form of air, will be supplied. So they need coke particles, air, and supply they also supply ore particles, iron ore particles, iron ore particles. So here we need air and we need coke particles, and the particle size has to be smaller for the efficient combustion. For the efficient combustion. So what they do, this coke particles stored in silo will be transported, with help of air, with help of air, with help of air, and air and coke particles enters into this furnace. Air and coke particles enters into the furnace. With help of bucket elevators, they feed ore particles. With help of bucket elevators or belt conveyors, they feed the ore particles. So the ore particles, coke particles when the ore particles goes into furnace, coke particles with air also goes into furnace, and oxidation, heating, melting of iron ore, everything takes place in the blast furnace. So this way, where we need to use oxygen or air for transportation as a part of process or excluding the part of process, we can use the pneumatic conveying. Do you all understood the example, what I'm trying to explain? Why do we need to use pneumatic conveying in this case? Students, do you understand?
It's for the transport of coal, right?
Yes, yes.
Yes, sir.
So thank you. So this is one industrial example I have showed where they use pneumatic conveying, for the transportation of coke particles in the blast furnace. Okay, so what are all required for the pneumatic transport? What are all the required for pneumatic transport? One is a closed pipeline. One is a closed pipeline for the pneumatic transport, and we have the uh, feed, solid feed. So the particles will fall in this one. Then we need to pump air. We need to blow the air. So we need a blower or compressor. Blower or compressor, right? To blow the air. So every blower can send the air with certain pressures. Every blower or convey compressor can send air with certain pressure. With certain pressure. If you want to blow the air with high pressure, it requires high energy. If you want to blow the air with low pressure, it requires low energy. That is the only parameter important, or that is only important thing. So the pressure, with what pressure you wanted to send, with what pressure you want to send the air, with what velocity you want to send air, determines the energy cost. Determines the energy cost. So we need to determine what is the diameter of the pipe, okay, and we need to determine at what velocity we are sending the air into this. So when you want to design a pneumatic conveyor, what is the pipe size, diameter of the pipe, with what velocity we are blowing the air, with what velocity we are going or we are sending the air. Another important thing is, as the fluid flows in the pipeline, what will happen? What are the important energy losses will take place? What is the important energy loss will take place? Pressure losses. That is delta P. The pressure loss delta P. So every blower can give certain amount of pressure. That means it is only efficient for a certain amount of pressure drop. It is only efficient for certain amount of pressure drop. So for a given amount of feed, we should be able to specify what is the diameter of the pipe, what is the velocity of air, and at these conditions, how much pressure drop it is causing. We should be able to estimate whether this pressure drop is within the limits of the required is within the limits or not. We have to mention. We have to show it. So the design of a pneumatic conveyor involves how much diameter of the pipe we need to use, at what velocity we need to blow the air. That determines the blower capacity. At what capacity of the blower we need to select depends on the at what velocity of air we need to pump. Now, with these conditions, how much pressure drop this can cause. Whether this pressure drop is within the blower limits or not, we have to check. Whether this pressure drop within the blower limits or not, we have to check. So these are the four important parameters we need to consider when you want to design the pneumatic conveying. What is the pipe size? What is the velocity of air? Based on the velocity of air, what is the blower capacity required? And based on the blower capacity, based on the pressure drop estimations, whether this is within the blower limits or not, we have to also determine. These are the four important parameters we need to take into consideration. Okay, so most important thing is velocities and the delta P. Velocity and delta P. So for pipe diameter, we have the standard pipes. We cannot just take whatever pipes we want, because the pipe manufacturers only manufacture the pipes with certain sizes like half inch, 3/4 inch, 1 inch, 1.5 inch, 2 inch. They make in this way only. They will not make whatever size we want. 1 meter, sorry. If you want 2 centimeters, 3 centimeters, they cannot make. They will only make with the standard, because then only we always follow standards, right? So that it can be used in the large scale. So we have the standards pipe sizes. From that we will select any one. Now, important thing is velocity. Important thing is, as I said, velocity and delta P. Why is that they are important? We will discuss now. Why is that they are so important? We will discuss now. So, so let me explain a case. So this is the pipe, okay? And in this pipe, right now we talk about only dilute pneumatic transport. We'll only talk about dilute pneumatic transport. In the dilute pneumatic transport, the solids are dispersed in the air and they are flowing easily. The solids are dispersed in air and they are flowing easily. Okay, so this is a horizontal. There are two types in the dilute pneumatic conveying. There are two types in the dilute pneumatic conveying. One is horizontal, another one is vertical. Another one is vertical. So I'm right now talking about only the horizontal pneumatic transport. I'm not talking about the vertical pneumatic transport. Okay, so but both are interrelated, and I will also explain. I will also explain the vertical transport also. So here we all know in fluid mechanics is the faculty taught delta P expression, Haugen-Poiseuille's expression. Students in the fluid mechanics course have you learned about pressure drop equation? I think third years definitely no, second years. When a fluid flows through a pipe, how do you estimate the pressure drop expression? No? Haugen-Poiseuille's equation. Delta P equal to 32 nu VL by D. So, okay, don't worry about that one. So, delta P is proportional to velocity and inversely proportional to diameter. Inversely proportional to diameter. So, that is the simplest expression. That is the simplest expression. Now, why there will be pressure drop when fluid flows? Let's say this is a pipe. There's a pipe and the fluid is flowing. Can anyone say why there will be delta P? Why there will be some delta P? Can anyone say? Let's say there's a pipeline, and in this pipeline, air is flowing or water is flowing, and as the fluid moves, there'll be always pressure drop. Another way, the fluid can flow from high pressure to low pressure. Unless there is some pressure drop, the fluid will not flow. That's what we learn in the fluid mechanics. Why is this? Why this pressure losses takes place when the fluid flows? Why is that pressure losses will take place? Sorry, I could not hear.
Sir, check from the walls.
Because of walls. What is that?
Sir, friction from the walls exerts force on the boundary layers and it propagates to the center. So we need to overcome that, and that's why the pressure gradient is required.
Very good. I think you gave right explanation. Perfect explanation. There is the when the fluid flows, there will be resistance offered by the wall that propagates into the middle. Because of that friction between the fluid and the wall, because of that friction between the fluid and wall at laminar conditions, laminar flow conditions, there will be energy losses. That energy losses is characterized as a pressure losses. If there is a turbulent flow, not only the friction between fluid and the wall and friction between individual layers of the fluid also takes place, right? That because of the frictional losses, the interaction between the wall and the fluid, interaction between the fluid and fluid particle causes friction. That frictional losses causes the pressure losses, and that is basically the important energy losses in the fluid flow. That is the important energy loss in the fluid flow. If energy losses are higher, you have to spend more amount of energy, right? That is basically cost. You need to spend more and more amount of cost for that transport of the solids. That's why we always want less amount of energy losses so that we can reduce the cost of the operation, the cost of the process. So as we rightly saying, the interaction between fluid particles, so fluid and the wall, is basically causes the friction. If velocity is higher, obviously the interaction will be higher and the frictional losses will be higher. For a given velocity, if the particle diameter is smaller, there will be less space and there will be less space, so the interaction also will be very higher. That's why it's inversely proportional to the diameter, right? So so here if I plot pressure drop with velocity, in y-axis I am taking delta P, in x-axis I am taking the velocity. Let's say the particles are free flowing, and the pressure drop, let's say this is the point. So this is the point at this high, since we are blowing the air at high velocities, the particles are suspended, and this is the pressure drop. And this is the solid feed, right? The solid we are feeding the solids here, and we are feeding the air here, gas here, air here. And let's say I haven't reduced the solid rate. I haven't changed the solid rate, but I have reduced the velocity. What will happen to pressure drop? I haven't changed the solid rate, but I have reduced the velocity of the fluid. What will happen to the pressure drop when I reduce the velocity in this direction? When it is velocity in the direction, can anyone say what will happen to the pressure drop?
Pressure drop will be less.
Yes, the pressure drop decreases. Very good. So when you keeping the solids rate constant, I'm reducing the velocity of the fluid, the pressure drop reduces. Now, will there any behavior of the solids will change if I reduce the velocity, keeping the amount of solids constant? Will there be any behavioral change of the solids? So what I'm trying to say, this is the pi. I have, let's say, this much amount of solids. I blow with high velocity like this. Now I'm reducing the velocity. One is pressure drop decreases. What else will change? Will the dispersion will be same as before, or dispersion will not be uniform, or dispersion will be uniform, or will be same? Will there be any change in the dispersion of the solids in the pipeline? Can anyone suggest? We all visualizing. There's a pipeline. We are putting the solids. We are sending the air. Now I have a completely uniform dispersion state. Now I'm keeping the solids rate constant. I'm reducing the velocity of air. What will happen to the dispersion of solids? Will it be same as before, uniform, or the uniformity will be reduced?
The uniformity will be reduced.
Yes, the uniformity of the solids will reduce because we are reducing the amount of air. And why particle is floating, dispersing? Because of the buoyancy offered by the air. When you reduce the velocity of air, the buoyancy will also reduce, and the drag will also reduce. Hence, the dispersion will be reduced. So, if you see at this state, the particles are, so these are the particles, uniform. As you reduce velocity, the particles tend to come close. Still, some amount of dispersion is possible, but the uniformity will be reduced. But at some point of time, if you keep reducing velocity, what will happen? The amount of air is not sufficient for the dispersion of particles. At some point of time, amount of air is not sufficient for the particles to disperse. At that time, what will happen? The particles
The
tend
blockage
to
will
settle.
take place.
Yes, definitely blockage. But before blockage, I'm coming to the intermediate stages. This called before leading to blockage. What will happen is that small amount of particles will tend to settle. Okay, that state, the starting point at which the particles tend to settle, that state is called salting. SALTIN. Space is not sufficient. That state is called salting. SALTING. That state is called salting. If you reduce further, what will happen? When you reduce further the salting velocity, what will happen because of this blockage? Because of this blockage, the velocity will tend to increase, because we all know the cross section area, when the cross section area is reduced, the velocity will increase, right? When the cross section is, since some portion of the pipe is occupied by the solid particles because of the settling or salting, suddenly the velocity will rise. Because the velocity rising, the pressure drop will also rise. If you reduce further, more amount of settling will take place, and reduce further, more and more settling will take place. That will lead to the blockage. That will essentially lead to the blockage. So I'm explaining three states here. At the condition at this point, all the particles are uniformly dispersed because of the high air velocities. As you reduce the velocity of air, the particles come close. And attain less dispersion. But the velocity will gradually linearly decreases. But at some point of time, velocity is so low that the particles tend to settle down. That state is called salting state, salting velocity. And when you reduce velocity further down the salting velocity, more and more amount of deposition will take place. That will increase sudden rise in the pressure drop because of the increase in the velocity gradients and turbulent gradients. And if you reduce further, and more amount of solids will settle down, and that will lead to the blockers of the transportation line, the blockers of the conveying line. So, what is the important outcome here? If we can predict salting velocity, the velocity of air in the conveyor should be higher than the salting velocity. Do you agree with me? If you want to transport solids uniformly, the velocity of air in the pipeline should be higher than salting velocity. Do you all agree with me?
Yes, sir.
Yeah.
Yes, sir.
Yes, thank you. So now how do we determine the salting velocity? That is the important thing now. How do we determine the salting velocity? That is the important. Now, the salting behavior is very, very complicated in the sense, although the phenomenon is very simple, predicting that condition theoretically almost impossible, because that is depends upon predicting that theoretically is almost impossible, because it depends upon the type of material, it depends upon the cohesive nature between the particles, also depend upon the shape of the particles, and also depends upon sometimes salting takes place, right? After some time they tend to redisperse. Back into the air. So people have tried to get, but very, very hard to find out exact theoretical correlation. So one of the important thing here I wanted to say, you all know it, but I wanted to re-emphasize again that some of the actual phenomena cannot be truly explained by the fundamental processes what we have learned so far, especially in 10+2 or before. So we difficult to explain most of them from the basic fundamental theoretical concept. Getting a mathematical expression would be very difficult. Whenever there is such problem occurs, when we cannot determine or and determine expression theoretically from the fundamental aspects, we use empirical relationships. Because empirical relationships are from the experimental evidences. So since this is a complicated process, identifying the salting system is a complicated case, people have derived certain empirical expressions to find out the salting velocity. Okay, so I will just give the expression for salting velocity. Yeah. So salting velocity is, there is an empirical expression derived by Rizk, R-I is a scientist name, R-I-Z-K, Rizk. He found out this empirical relationship, that is MP, mass flow rate of particles. MP is mass flow rate of the particles by density of the fluid, salting velocity into area of the pipe, is equal to 1 over 10 to the power of 1440 times x. X is the particle size. This is, sorry, we didn't come up well. This is x. X is the particle size plus 1.96. 1.96 into saltation velocity by root of g, that is gravitational constant, into diameter of the pipe. Still we have the power, and I will give this actual expression. As I said, I will share the book after the class. In that book, this empirical correlation is also there. In that book, this empirical correlation is there. So using this empirical correlation, we can find out the saltation velocity. Even after doing the lot of experiments and deriving this empirical correlation, they could figure out that this is only 60% effective. 60% effective. That's why since this is not highly efficient, still people uses this US saltation velocity. So the actual velocity of the air in the pneumatic conveyor will be almost 50% higher. That is 1 point, you will always have to multiply with 1.5 times to get the velocity. So the velocity of the air in the conveyor should be 1.5 times, that is 50% higher than the saltation velocity, because the prediction of saltation velocity is not very efficient. And this is the best you could find out from the literature, or people could derive the relationship. Okay, we all understood. I have explained the saltation condition, and since theoretically we cannot derive, we have to use empirical relationship, and empirical relation developed by Rizk is this one, and this is only 60% effective. Hence, the velocity of the air in the pneumatic conveyor should be, or has to be, 1.5 times, that is 50% higher the saltation velocity. Students, do you understood what I'm trying to say? Or do you have any questions at this point? Okay. I assume that you're understanding. If anyone don't understand, kindly let me know. Otherwise, moving forward will not be no use without understanding. So that is for the horizontal transport. Now, what about vertical transport? What will happen in the vertical transport? What will happen in the vertical transport. Okay, so let me explain a simple phenomena. So this is a vertical pipe. This is a vertical pipe. Here we have a plate. Usually they call distributor plate. Distributor plate. Basically, this is a perforated disc. Basically, this is a perforated disc. Very, very small perforations. A punching disc like that. This is not solids, okay? This is a perforated disc. These are all perforations, small, small holes, perforations. This is a distributor plate is like this. A circular plate with perforations, small, small holes, perforations. Okay. So why do we use this perforations? Sorry. Perforations, and here we have an inlet, solid inlet. So through this solids will fall. Through this solids will fall. This is a solids. Solids will fall. So and air will be blown from the bottom. Air will be blown from the bottom. Let's say you have fed some solids and all the solids students, when did it disconnect? When did I got disconnected?
Sir, 2 minutes back, if you can repeat.
So is there that empirical correlation have you seen?
Yes, sir. Sir, the
So
whole part you are.
sorry.
The vertical.
Yes, sir. So
Oh,
the
when I start
distributor part.
vertical.
Yes, sir.
Oh, right.
So the distributor part.
Sure. I will go back and you able to hear clearly and understand what I'm trying to explain. Right. Suddenly got doubt. Yeah, share screen. Start now. I hope you're able to see now.
Yes.
Are you able to see my screen?
Yes,
Yeah.
sir. Yes, sir.
Yes. Thank you. So in the vertical pneumatic conveyor, we have the vertical pipe, and here there will be a distributor plate. Distributor plate is nothing but a circular metal plate with perforations. These are all the small holes. And kindly record, okay? Someone who is doing the record, kindly record. So these are the distributor plates. Now, to this distributor, in this vertical pipeline, there will be a hooper or a funnel through which the particles, the solids will be fed. The solids will be fed. So when you feed the solids, they come here and nicely settle down on the distributor plate. If you don't have distributor plate, what will happen? They will fall down. They will continuously fall downwards. So to make a stable platform for the particles to not to flow down, there is a distributor plate. So when you blow air with velocities, high velocities, usually velocities greater than 20 meter per second. But however, this is depends upon the size of the particle. If the particles are very, very small, you don't have to go for 20 meter per second. If it's micron size particles like 50 micron or something, definitely we need velocities of 20 meter per second. So when you blow air at this high velocity, the particles are suspended. The particles suspended and move along with the air. Move along with the air. Move along with the air. So move along with the air. That way, the transportation of solids in the vertical pneumatic conveyor takes place. Vertical pneumatic conveyor takes place. Right? Now, what will happen, just like in a horizontal pneumatic conveyor, when you keep the solid loading constant, and keeping the solid loading constant and reduce the velocity of air, what will happen? Let us see that. What will happen? Let us see that. So here I have similar like before, delta P versus velocity. Delta P versus velocity. Let's say at high velocities, like before, and the particles are uniformly dispersed and pressure drop is higher. Keeping the solid load constant, if I reduce the velocity, same as horizontal pneumatic transport, even in the vertical transport, the pressure drop will reduce. The pressure drop will reduce from the at this point where we have the uniform dispersion high velocity. Now, as you reduce it, what will happen? We all know it. As you reduce the velocity, this is the particle, and the air is blowing like this. Air is lifting the particles like this. Then we know the gravitational force acts downwards. Whereas buoyancy force and drag force acts upwards. You will learn drag force later in the fluid mechanics course, and please, you have to wait a little bit, some time to understand this, right? So drag force acts. When I reduce the velocity, the force offered by air, definitely reduces. The force offered by the air definitely reduces. So because of that, what will happen? What will happen? Can anyone say? What will happen in the pneumatic conveyor? Let's say at this scale, what will happen? Someone is saying, but I could not hear. Can you say again?
So the particles will precipitate.
Yeah, they tend to
Precipitate.
settle. Yeah. So as we do realize velocity, let's say at this velocity, this much height, up to this height, let's say the particles are moving. When reduced velocity, the height of the particles will reduce because they tend to settle down. The particles are tend to settle down. At some point of time, okay, the particles come so close. The particles come so close. The particles come so close that air is only flowing between the particles. Air is flowing between the particles rather than lifting the particles. The air is flowing between the particles. Major amount of air is just pushed in between the particles. Very less amount of air is used for the pushing of the particles, for the transportation particles. So that point is called choking, choking, choking velocity. Like salting velocity, that velocity is called choking velocity. If you reduce velocity further down, suddenly the pressure drop will increase. If you reduce the pressure, if you velocity down, pressure drop will increase. So the choking condition where the air is, instead of lifting the particles, air is only flowing between the particles and less amount of air is used for the pushing of the particles or transportation of the particles. So just as we have the empirical correlation for the salting velocity, we also have the empirical correlation for the choking velocity. So the actual velocity of air in the pneumatic conveyor should be 1.5 times the choking velocity. Should be 1.5 times of the choking velocity. So we have an empirical correlation. I will write this empirical correlation, but like I said, I will provide the book. In that book, this empirical correlation is given, and you all can clearly see that. So UCH, choking velocity, by wide fraction in the wide fraction of the choking conditions minus terminal velocity. I will explain about wide fraction at choking terminal velocity equal to G by G is nothing but mass flux. Mass flux. Mass flux. Right? Mass flux is nothing but mass fluid of the particles or mass fluid by area. Mass flux is nothing but mass flow rate per unit area. Mass flow rate per unit area into density of the particles into 1 minus void fraction at the choking conditions. Void fraction at the choking conditions. Here, we don't know void fraction choking condition. We don't know void fraction choking condition. We also don't know choking velocity. We don't know void fraction value, and void fraction I have also showed. I explained like this is the pipeline, and these are the particles that dispersed. So this pipeline is filled with particles and voids. Voids nothing but the spaces between the particles. So the void fraction nothing but the voids volume, the total voids volume, the free volume, solid free volume by the total volume. The void fraction nothing but voids volume, solid free volume by total volume is nothing but the void fraction. So we don't know void fraction, we don't know choking velocity. So if you want to solve two variables, definitely we need two equations. So there have been another important empirical correlation, that is density of the fluid to the power of 0.77 equal to 2250 into void fraction at choking conditions minus 4.7 to the power of minus 4.7 minus 1 by use choking velocity by epsilon of choking velocity, choking conditions by ut. U terminal velocity. Sorry, the equations are so big and looks awkward, but I will provide the book. In the book, we have. I can also prepare PowerPoint. I will also show you in the next class. So, using by solving these two equations simultaneously, we can find out the choking velocity. Once you find out the choking velocity, the velocity of air in the horizontal or vertical will be 1.5 times the velocity of this one. Now, what is there are important parameters which in the previous expression that is called terminal velocity. There is an important expression. I'm sorry, one variable, one is called terminal velocity, which I didn't explain so far. So let's say this is the vertical pneumatic conveyor, and we are blowing air. We are blowing air. Okay. We are blowing air, and these are the particles. These are the particles. So imagine that. Just imagine that I have sent air. I'm sending air at low velocity, very low velocity. That let's say choking velocity. At choking velocity, what will happen if I send air at choking velocity? The air will take a path between the particles and flow like this, because air doesn't have enough energy to lift the particle. Air doesn't have enough energy to lift the particle. If I increase velocity, if I increase the velocity higher, if I increase the velocity higher, at some point of time, what you'll observe is that, right? I'm just, this is low velocity. Let's say I am putting medium velocity that is slightly higher than the choking velocity. At that time, what we'll see that the particles tend to move slowly. The particles tend to lift, just suspend. The particles are just suspended in the air. The particles are just suspended air, and the particles are rotating wherever they are. Wherever they are, they're just rotating in the air. This condition is called minimum fluidization. Minimum fluidization. FLUIDIZATION. Minimum fluidization. So at minimum fluidization conditions, the particles are just suspended and rotate wherever they are. If you increase velocity further, what will happen? Since we already crossed the barrier, that is the air is able to lift the particle. If you increase higher, what will happen? The particles are lifts upwards much more. If the particles will go certain height, they will move up to certain height. They will move up to certain height. If you increase much more high velocity, they just go along with the air. Wherever they go, they just go along with the air. And that the particles will attain certain steady velocity. The particles will attain certain steady velocity. So here the particle velocity is almost zero, and air velocity have certain value. And here the particle has certain velocity, the air has certain velocity, the particle has very, very low velocity because started moving. At this condition, the velocity of air is very high, the particle velocity is also increasing. As you increase the velocity of air, the particle velocity will increase. But at some point of time, even if increase the air velocity, the particle velocity will attain certain constant value, and the particles will move with a certain value. That velocity is called terminal velocity, steady velocity, either steady settling velocity or the steady velocity at which the particles are moving along with the air, which is called terminal velocity. That is called terminal velocity. So for the this condition before attaining terminal velocity, this condition is called fluidization condition. Before it attain terminal velocity, uh, this condition is called fluidization. FLUIDAZATION, fluidization, the fluidization condition. So fluidization itself is a big concept. I will not touch that in this course because it's not part of this course. So that's why I will not get into fluidization. I will just stick to the pneumatic conveying only. So one important criteria people have identified that if you want pneumatic conveying, dilute pneumatic conveying to be takes place, velocity of the fluid minus velocity of the particle. This is called slip velocity or relative velocity. This is also called as slip velocity or relative velocity. Relative velocity. This has to be equal or greater than this terminal velocity. This has to be equal or greater than terminal velocity. Then only easy dilute pneumatic conveying will take place. That is what people have observed. Although once particle attains terminal velocity, the particles will move at steady velocity. But for actual practical conditions, this relative velocity has to be equal to terminal velocity. Then only easy smooth dilute pneumatic conveying takes place. Right? So I have talked about pipe sizes, as I said, standard pipe sizes. Then I talked about what velocity we need to use. Then I have defined two important conditions called choking condition, salting condition, and how to determine that, and what velocity we need to use in the pneumatic conveyor, which I explained. In the next class, I will talk about, as time is over, I will talk about how to estimate this pressure drop, and how to estimate this pressure drop. Then we'll solve few problems on designing the pneumatic conveyor, dilute pneumatic conveyor. Then I will go to the dense pneumatic conveyor. Dense pneumatic conveyor. Very brief view of the hydraulic conveying, which I will discuss in the next class. So, first of all, I'm really sorry. There is some disturbance with this tab and pen and annotations. Hope you're able to understand what I have written so far. So you all please read the book which I'm going to upload. And if you read the book, if I listen to my class, you don't need any additional notes. The book itself will be I have given a very detailed explanation of the book, so you'll be able to understand. If you think you need a different notes, I can prepare notes and send it to you also, like PowerPoint. So any questions do you have? Student, do you have any questions based on today's class? Hope you are still alive. Network connection. Student, do you understood today's class, or how do you feel?
Yes,
Aryan,
sir, understand.
Yes, sir,
Okay.
understood. Sir, but the annotation that you were using, sir, your handwriting was not clear to me. Means I
Yeah,
cannot
very
understand.
bad. Yeah.
Yes, sir.
Sorry. Actually, I'll prepare PowerPoint. Actually, what I thought, the particle movement, the settling, salting, I thought annotation will be more easier, but this tab and pen and all interacting so badly when I share. Actually, when I'm not sharing it, they're writing very well. But once I started sharing, things are changing. Maybe class strength or Microsoft Teams, I don't know. So I'll prepare
Sir,
PowerPoint.
actually, you need time to practice on writing on the iPad. Sir, it takes time around 3 to 4 days. You have to practice on the iPad to write. Then only it will come.
Actually, without sharing in the Teams, I've practiced because my kids draw a lot of images and all on this tab only. So I used to show them how to draw and all. That's why I was a little bit confident. Yeah, but I think I could understand that my confidence level is very low, or my practice level is very low. What happened? Lot of smiles coming. Okay. Any questions? We have 2 minutes. Any questions you have, I can take it.
Sir, have you updated the marks of the test?
So I haven't updated because there is some glitch happened. I'm still exploring. That's why I haven't updated the marks. So that I will. What happened? Some of the clever students, when I asked them to join the test with their name, they have joined with some fake name. Then they have finished the test. One mistake I did that I thought it would be useful for you to show answers, but that is the way they have cleverly misutilized. Probably gift to me on the next day of Teachers' Day. So they actually first saved with a fake name, then they got the answers, then they again started the test with the actual name, then they actually used actual answers to fill the quiz. This is not one or two, many students. So these are the, I kindly stop that one. Claps and laugh and other thing.
So then how to resolve the problems?
That means,
Resolve the
but you,
problem is,
Yes, sir.
I'm actually getting the
Another
IP
test on
address.
MS Forms.
I'm getting the IP address of the students who actually did this. I have already sent request to that. They haven't get back to me till now. If they give me IP address and when they joined, who joined at what time, and relatively I can predict it. But if you cannot predict it, I have to conduct the retest. That is the only option.
sir, means you have the access when the student has joined. So from that you can know who has done
They
this.
don't. They're not providing by default. That's why I have contacted the platform people. It's not by default. It is not there. If it is there, I could have easily figured out.
So you can
That is
ask
why.
for the screenshot also that we have taken at the last. Then that proof will remain.
But now
But
it's over
sir,
now.
not. Yes, sir. We haven't take screenshots.
Now I cannot ask. Once test is over, I cannot ask. I cannot blame some good students. I cannot say, I cannot trouble them. So I'm just, if I cannot figure out, then I will have to conduct retest.
Sir,
There is no other way
maybe
for me.
failing them, you could obtain the IP
The
addresses
retest will be
that
better.
are
The
logged in.
retest will be better.
Sir, retest will be better.
So definitely, I think I have to do that. So next exam, when we have the next exam, right? We have next month, I guess, according to the academic calendar. At the time, the previous portion and current portion will be together. I will give.
So, sir, like, will there be two tests or will there be one test for that?
There will be one test for both previous portion, what I've discussed, and currently what I'm discussing. Together will be there, but there will be one test. I will not, because if I use classes for the conducting test, I will have very less hours actually. And that's why I will have to conduct together one test. So instead of 3 tests overall, there will be only 2 tests. So good thing is that those are good students. They already know what kind of questions I'm giving because you already didn't test. I have given maximum possible questions in that previous test. So you already know what kind of questions will come from the previous portion. That way your preparation can be easier. So what I'm teaching now, that will be there currently, like in the next test will be 3 parts. One is storage of solids, transport of solids, and the fine particle classification. These are the 3 topics I'm going to cover by the next test. So on all the topics, we will have a test. And I have to either stick to the themes or I have to try with that module. Either of these 2 platforms, many students are listening. So I will not use that quiz platform. I can still use it because I can opt out showing the results. I can still do that, but I don't want to take any risk.
Sir, but
Okay,
I was saying that the test actually had some wrong answers given as right. So, like, if people are scoring by doing that method, then obviously they must have gotten all those answers wrong, which were
Yes,
actually
sir.
correctly solved
Yes,
by
sir.
hand.
So
No, I
they
agree.
must have got the full marks also.
Sir, retest will
No,
be
no,
better, sir,
they
cause
are
like
clever.
many people
No
just
one actually answered all. Even if they know answers, they haven't scored full because they know that I will figure out. So they only got 80%. Some students don't use brain in learning. They use brain in these things. So they're very clever and difficult to catch a thief. We have to. I can put effort, but that will, if I, instead of wrong person, if I trouble some good person, they will get hurt, which I don't want, especially in the online platform. Person to person, we can figure out. But while discussing online, instead of a wrong person, if a really good student, if I catch him and trouble him, he will feel hurt and it will stay in his heart for a long time, which I don't want. As a common notation, I may not able to catch wrong people, but I don't want to hurt right people. That is why I'm just taking back step. Even for your seniors, at the time class 10th is 40, I have caught who did mistake. I have showed everything. I have emailed everyone what are the mistakes and everything. But large group, there is a high chance of doing a mistake. That's why I'm just worrying because I don't want to hurt the some of the good students because it will affect all exams, everything, the whole. Because online means itself is sensitive. All of us already at certain stress levels. I don't want to put further any additional trouble. That's why I'm trying to look for an easy solution, which will not trouble you and which will make your life smooth. That is only my concern.
So the next test, so it won't be like a retest. It'll be like next test will have cumulative syllabus.
Yeah, that is true. Vikram, you're right. It will be a next test only. It won't be a retest, but this portion also will be included. The previous portion also will be included.
So, sir, this test marks would be discarded.
If I cannot figure out, okay, I'm still trying different ways. If I cannot figure out, then I have to discard this test.
Sir, means will you send an email regarding what the conclusion you have reached
I
after?
will announce in the class now. Why email?
Okay, sir. Yeah, fine.
Problem with email is that it is going in 7 different emails. Because strength is high, when I have to send to ERP, it's at one point of time not able to go. Okay, guys, thank you so much, and hope you all understood today's class. I will upload the textbook, and please read and please read before you attend next class.